We are Ivan and Juliet from Google Research, and today's talk will be about how we implement DICE attestation on AMD SEV-SNP. Let's quickly go through the agenda. First, we will talk about Project Oak. Then we'll talk a little bit about how remote attestation is done on AMD SEV-SNP. Then we'll discuss our DICE solution for SNP, and we'll show you a remote attestation demo. But first, let's quickly discuss what Project Oak is. Project Oak is a research project at Google aimed to make it possible for data owners to reason about how their data will be used by the server in the ways that are verifiable by external reviewers. And we're developing a secure framework for processing private data that provides hardware guarantees and can be remotely attested from a client device. Next slide, please. In order to achieve this, we are using several building blocks. First, Oak Framework supports running server workloads in trusted execution environments, or TEs. Second, Oak supports remote attestation, which provides client devices with hardware-backed claims about the identity of the firmware and software that runs on the server. And third, transparency, meaning that Project Oak is open source and reproducibly buildable by external reviewers, which makes remote attestation meaningful because these reviewers can link the software identity that they have received during the remote attestation back to its source code. And we're also incorporating external verifiable and append-only logs, where we put every single version of Oak binary that was deployed on the server. This ensures clients that a malicious insider won't be able to perform targeted attacks where one individual client is being connected to a malicious server. Next slide. And okay, in the next section, we're going to describe main ideas behind AMD SEV-SNP attestation process. But first, a quick reminder about what a remote attestation is. Remote attestation is a process that allows clients to establish trust in remote workloads. And the main idea is that the server provides clients with a set of claims about the firmware and the software that runs on the server. And this set of claims is often called an evidence. And a remote client can verify this evidence in order to understand what server workload it's trying to connect to. This evidence should also be endorsed by the hardware manufacturer so that the client can be sure that it's connecting to a legitimate server. And in order to verify the evidence, clients often have expectations about claims that they should receive from the server. These expectations are often called reference values. These values can be compared to the claims that the client receives from the server in order to establish that the server runs the expected workload. And after the verification is done, this client can, for example, establish a secure session and send its private data to the server. Next slide. Okay, AMD SEV-SNP is a hardware technology that implements trusted execution environments. And such environments are provided as secure VMs, whose memory pages are encrypted with the hardware key embedded inside the CPU. Such memory encryption protects the VM from the hypervisor because the content of the memory pages is only being decrypted inside the CPU. This also means that a potential insider that has physical access to the machine and can eavesdrop on the memory bus is unable to access plaintext data. AMD SEV-SNP also provides the ability to perform remote attestation by taking a measurement of the VM workload and signing it with the hardware key. AMD also provides certificate authority servers that can sign the corresponding hardware key by creating a chip endorsement key certificate. This means that AMD becomes the root of trust and removes the need to trust the server owner. Next slide. Okay, AMD SEV-SNP provides remote attestation by generating a special data structure called an attestation report. This report contains information about the firmware and measurements of the VM memory, and it is also signed by the hardware key. And guest VM that is running under SEV-SNP can request such report from the security processor located inside the CPU. Also, the corresponding host can request a so-called versioned chip endorsement key certificate, or VCX certificate, from a remote AMD server. The certificate signs the corresponding hardware key that is used to sign attestation reports. VCX certificate and the attestation report together form an endorsed evidence that is represented as a certificate chain going all the way to the AMD root certificate, which can later be sent to the client for verification. And since the client has all expected measurements of the VM memory and the AMD root certificate, it can first verify the VCX certificate and then verify that the remote attestation report contains all expected measurements, thus establishing trust in the server workload. Next slide. As we previously discussed, AMD SEV-SNP attestation report contains information about the firmware, such as the TCB version, and also the measurement of the VM memory. And even though guest VM can request an attestation report at any time, it will always contain the measurement of the initial state of the VM, since this measurement is taken only once before the VM boots. This measurement is calculated as a hash of all memory pages in the initial VM memory layout, together with the vCPU state and some additional information. For example, addresses of memory pages for storing secrets. This means that the attestation report doesn't contain the information about the full VM workload and only has the initial VM memory map. Another interesting field in the attestation report is the report data field, which can be used by the guest VM to put any data that will be signed by the hardware key once the report is generated. While other fields in the report are already finalized by the time the VM boots, the report data can be specified at any time when the guest requests the report, which may be useful for binding runtime secrets to the VM identity. For example, guest can generate an encryption key pair after the boot that should be used to create secure sessions with clients. And in this case, the guest can put the hash of the corresponding public key into the report data field and then request the attestation report, which will result in a certificate that signs the encryption public key and thus cryptographically binds client secure sessions to the VM identity. This, for example, helps preventing time of check versus time of use attacks, where a client receives a report from a legitimate VM, but after successfully verifying it, is redirected to a malicious VM. Next slide, please. Okay, one of the problems with only providing the measurement of the initial state of the VM is that clients have to assume without any evidence that the VM has booted correctly and no malware was inserted during the boot process. So in order to gain trust in the server workload, the client needs to get the measurement of the entire workload and not only the initial state. Meaning that to increase the client's assurances in the VM's security and privacy, we need to provide clients with an evidence containing the complete server workload. Next slide. And one of the existing technologies for providing measurements of complete server workloads is called measured boot. In measured boot, each software component that is loaded into the server's memory can perform a measurement of the next component, which in the end will result in a combined measurement of all components of the server workload. For example, before loading the bootloader, BIOS will get a measurement of bootloader's code and configuration and store it in a specified location. Next, once the bootloader starts, It will do the same for the operating system before loading it into the memory, and so on. And later, this combined measurement can be sent to the client for verification. This technique provides more assurances about the server's behavior because the measurement contains every single step of the boot process and also the entire operating system, while the measurement of the initial state would just contain the BIOS. And an additional note, in order to provide integrity protection for such measurements, they are often stored in a specialized device called Trusted Platform Module, or TPM. Next slide. Okay, in the next section, we'll talk about how we apply measured boot to our TE solution. Next slide. One of the existing architectures that provides measured boot solution for multi-component systems is called Device Identifier Composition Engine, or DICE. And the main idea behind DICE is that the integrity of such measurements is provided not by specialized devices, but by a certificate chain. In DICE, each layer, which in DICE terms is a name for a software component, can load and perform a measurement of the next layer. And it also can issue a certificate that endorses this measurement, meaning that in the end, when all software components have been loaded into the memory, we will end up with a list of certificates that endorses measurements of the complete server workload. And the main point here is that these certificates are combined in a certificate chain using the way DICE generates certificate authority keys, the ones that are used to sign such certificates. In DICE, each layer is provided with a compound device identifier, or CDI, that is used to derive a per-layer certificate authority key. And the corresponding CDI value is generated using a key derivation function, which takes the current layer's measurement and the previous layer's CDI value, meaning that keys that are used to sign certificates are linked together, and they also depend on the complete workload measurement. And the root CDI value is derived from the unique device secret, or UDS, which is a device-specific secret that can be generated externally and embedded into the hardware. This means that only the device that knows the corresponding secret can generate all of the necessary keys. DICE architecture was originally created to attest IoT devices from an IoT controller. In this use case, the IoT controller knows all of the UDS values of the corresponding devices, which means that it can derive all of the necessary keys and verify corresponding certificates. Next slide. So, in order to solve a problem of getting a measurement of the complete VM workload, we can implement DICE for AMD SEV-SNP. But in order to do this, we need to build a certificate chain, which starts from the unique device secret. And here we are faced with a challenge. In TEs, we cannot use the UDS to derive secrets in a way that is verifiable by the clients, because the hardware key is a secret known only by the TE itself. So instead of deriving keys, we can generate an ephemeral key pair for each layer and sign it together with the layer's measurement, thus forming a certificate chain. On top of this, we will use the attestation report as a root certificate, because it already contains the measurement of the layer 0, and we also can use the report data field to sign the hash of the layer 0 ephemeral public key, meaning that in the end, we will have a certificate chain that is rooted in hardware. Also, an important note that this specific solution was inspired by the talk from Peter Gonda from Google Cloud, and here is the link to the talk. Okay, now I will give this presentation to Juliette, who will talk about our solution in more detail.
Thank you, Ivan. So, like Ivan explained, when the VM starts up, the firmware initially generates an ephemeral key pair. And then when it requests the attestation report from the hardware, it includes a hash of the public key in this request. This then means that the attestation report that is returned by the hardware includes not just the TCP version and the measurement of the initial memory, which includes the firmware, but also endorses this public key hash. This then binds the ephemeral key pair of the firmware to the hardware attestation report. And in our example, we have several dice layers on top of the hardware. The first one is the firmware that, like I just mentioned, and the other one is a restricted kernel, and on top of that, an enclave application that performs business logic. The firmware in our case is a custom vBIOS and bootloader that we've written, and it's about 10,000 lines of code. It's written in Rust, and its dependencies are reviewed. It's enlightened for SEV-SNP and DICE. The goal is to keep the TCP as small as possible, to make it as possible to make judgments about the VM. The next state, the kernel, is called the restricted kernel, and it's also a custom kernel written in Rust of around 15,000 lines of code. It is also enlightened for DICE attestation. You can learn more about it in the talk by Conrad Gerbler, who is also on our team at last year's OC3. And the nice thing about DICE is that it also adapts to different stacks. For example, as another solution, we have something called OC containers, which consists also of the stage level firmware, but on top of that running a Linux kernel and 2 system images that eventually load a Docker container. And in this case, the principle is the same, where each stage generates an ephemeral key pair, which is endorsed by the prior stage, and then it measures the next stage and endorses that key pair. And now we have a demo for verifying DICE evidence. First off, let's take a look at the evidence as it is returned by a real TEE running on a genuine AMD SEV-SNP CPU. We see here first the type of the platform, which in our case is AMD SEV-SNP. We see the remote attestation report, which is the report that is signed by the hardware initially, which includes the measurement of the firmware and also includes the hash of the public key that was generated by the firmware. This public key is then also included in the attestation evidence. Next is the layer for the kernel, which is signed by the private key of the firmware. This layer includes a measurement of the kernel as well as all of its associated configuration. It also endorses the private key for the kernel. Thereby, it acts as a certificate authority for the kernel. The kernel, in turn, then loads the application and measures it and provides it with encryption and signing private keys. For both of these keys, there exist certificate authorities, which again include the measurement of the application and its associated configuration. We can then also see the endorsements, which is sent to the client alongside the evidence. In this case, the TE certificate is a certificate issued by AMD that endorses the hardware's root key as being in a genuine AMD SEV-SNP TE. We then also will have certificates for both stage 0 and the restricted kernel and the application, which in this case act as an endorsement from the OC team as endorsing those binaries that we have released. It includes provenance of the binaries and also includes a signature of a verifiable log that attests to these binaries having been published. We have then built a tool to verify evidences And what this does is that it allows us to build the source code of all the components, so that it's the firmware, the kernel, and the application from source code, and take the measurement of the build artifacts. We see here that it returns the associated artifacts of the firmware measurement, the kernel image measurement, the kernel configuration measurement, and the application measurement. It then allows us to compare those measurements against the aforementioned evidence coming from a real TEE. And when it does, we can see that it first verifies that the attestation report is indeed signed by AMD, that there's a genuine AMD SEV-SNP TEE, and then it also checks that the attestation report endorses the root layer, which is the keys generated by the firmware, and that those in turn endorse the next layers. Lastly, it verifies that the hashes we have provided to it, that we've generated prior, match the evidence of the attestation evidence. This means that we can bind the attestation evidence coming from a remote workload directly back to source code, allowing the client to reason about the behavior of the workload. We can then also see a few possible attacks. For example, what might happen is that during transit, an attacker tampers with the attestation evidence. Say, for example, they replace the public key of the firmware, which will then allow them to forge the rest of the dice chain. So if we modify this public key and we attempt to verify again using the command generated by the verification tool, we then see that first off, it does verify that the report is coming from a genuine TEE that's endorsed by AMD. However, the root layer doesn't endorse the private key, and hence the rest of the dice chain is invalid. Another possible attack could be that an operator runs a different version of the software than the client expects. For example, there might be a malicious version of the restricted kernel, which would log dice secrets as part of boot up, which then would later allow us to impersonate the TEE. And we have built such a version of the restricted kernel, and we have again retrieved evidence from a real TEE running this version. If we attempt to verify this malicious evidence, we see that it does verify again that the attestation report is valid, and indeed it validates that the dice chain is valid, so the firmware endorses the kernel and the kernel endorses the application. But by the time we come to compare the measurement of the kernel to the expected measurement, it fails and says that kernel layer verification failed, since the kernel has a measurement different from what the client expects. And this then shows practically how to bind the attestation evidence coming from a TEE all the way back to source code. In summary, we've discussed dice attestation for AMD SEV-SNP, how to provide a measurement of the full workload, and we've shown our own minimal stack for a workload that allows us to reason about the state of the TEE. We've also shown the client verification logic. Thank you very much. You can take a look online at our repository. You can also clone the demo that we've just run as part of this talk and run it yourself. Thank you very much.